In the realm of machine learning, ML, selecting the right development approach is crucial for building effective models. This decision impacts the model's performance, scalability, and maintainability. The DP100 course, Design and Prepare a Machine Learning Solution, provides a comprehensive guide to navigating these choices. This presentation will delve into various development approaches, their advantages, and considerations to help you make informed decisions. Before diving into model development, it's essential to thoroughly understand the problem domain. This involves identifying the specific problem you aim to solve, the data available, and the desired outcomes. A clear understanding of the problem domain helps in selecting the most suitable development approach, ensuring that the model aligns with business objectives and constraints. Exploratory data analysis, EDA, is a critical step in the ML development process. It involves summarizing the main characteristics of the data, often using visual methods. EDA helps in understanding the data distribution, detecting anomalies, and identifying patterns. This step is crucial for selecting the right features and pre-processing techniques, which in turn influence the choice of development approach. One of the first decisions in model development is choosing between supervised and unsupervised learning. Supervised learning involves training a model on labeled data, making it suitable for tasks like classification and regression. Unsupervised learning, on the other hand, deals with unlabeled data and is used for clustering and association tasks. The nature of your data and the problem you aim to solve will guide this choice. Supervised learning approaches include algorithms like linear regression, decision trees, and neural networks. Each algorithm has its strengths and weaknesses. For instance, linear regression is simple and interpretable, but may not capture complex patterns. Neural networks, while powerful, require large data sets and significant computational resources. Understanding these trade-offs is key to selecting the right approach. Unsupervised learning techniques such as k-means clustering, hierarchical clustering, and principal component analysis, PCA, are used to uncover hidden patterns in data. K-means is efficient for large data sets, but requires specifying the number of clusters. Hierarchical clustering provides a dendrogram, but is computationally intensive. PCA reduces dimensionality, but may lose interpretability. The choice depends on the specific requirements of your task. Semi-supervised learning combines labeled and unlabeled data, offering a middle ground between supervised and unsupervised learning. It's useful when labeled data is scarce. Reinforcement learning, on the other hand, involves training models through trial and error, receiving rewards or penalties. It's particularly effective for tasks requiring sequential decision-making, like game playing or robotic control. Selecting the right model involves evaluating multiple algorithms to determine which performs best on your data. This process includes splitting the data into training and testing sets, using cross-validation, and assessing performance metrics like accuracy, precision, recall, and F1 score. Model evaluation ensures that the chosen approach generalizes well to unseen data, providing reliable predictions. Feature engineering involves creating new features from raw data to improve model performance. This step requires domain knowledge and creativity. Feature selection, on the other hand, involves choosing the most relevant features to reduce dimensionality and prevent overfitting. Techniques like recursive feature elimination and lasso regression are commonly used. Effective feature engineering and selection are crucial for model success. Hyperparameter tuning is the process of optimizing the parameters that govern the learning process of an algorithm. Techniques like grid search, random search, and Bayesian optimization are used to find the best hyperparameters. Proper tuning can significantly enhance model performance, making it a critical step in the development process. It requires careful experimentation and validation to avoid overfitting. Once a model is trained and validated, the next step is deployment. This involves integrating the model into a production environment where it can make real-time predictions. Considerations include scalability, latency, and monitoring. Tools like Docker and Kubernetes can help manage deployment. Ensuring that the model remains robust and performs well in a live setting is crucial for its success. Ethical considerations are paramount in ML model development. This includes ensuring fairness, transparency, and accountability. Bias in data can lead to unfair outcomes, so it's essential to use techniques like fairness-aware learning and bias detection. Transparency involves making the model's decision-making process understandable. Accountability ensures that there are mechanisms in place to address any issues that arise. Model development doesn't end with deployment. Continuous monitoring and maintenance are essential to ensure that the model remains accurate and relevant. This involves tracking performance metrics, retraining the model with new data, and addressing any issues that arise. Tools like MLflow and TensorBoard can aid in monitoring. Regular updates and maintenance ensure the long-term success of the model. Selecting the right development approach for building or training an ML model is a multifaceted process that involves understanding the problem domain, performing EDA, choosing the appropriate learning technique, and considering deployment and ethical aspects. By following best practices and continuously monitoring the model, you can ensure its effectiveness and reliability. The DP100 course provides a comprehensive framework to guide you through these steps, helping you build robust and scalable ML solutions.